All right, so last time we discussed how to deal with quadratic forms. And we said if the quadratic form given by this for symmetric matrix A could be understood by rewriting this in terms of processing the matrix and writing it as lower triangular with ones on the diagonal times D diagonal times the transpose of the lower triangular. And then we said you could regroup this and write it as, with a change of variables, just D multiplying L transpose X and then the transpose of L transpose X here. And so what we determined was trying to understand what the behavior of this quadratic form is given by thinking about what the diagonal entries are. Are they all positive? Are they all negative? Are some positive, some negative? Are some zero? Because basically, with this new variable here, you're just going to get a sum of squares for this thing times new variable I squared. So the signs of the DIs are going to tell you what this quadratic is behaving like. And so we had these words that I told you at the end of last time. Positive definite, positive semi-definite, negative semi-definite, indefinite. So basically positive definite means that all values of Q are positive whenever X isn't zero. So if you think about that quadratic function, what does it have, what sort of critical point does it have at the origin?
Global minimum?
Right, it's zero at the origin and strictly positive for all their X's, so it looks like a
Global
minimum. And this corresponds to all the D's, all the entries, all these diagonal entries are positive. It's negative definite means negative here, so all the D's are negative, and then it looks like a downward pointing paraboloid, so it's a max. If it's indefinite, meaning that it's positive for some X and negative for some other X, what does that say about the D's now?
They're mixed.
They're mixed, at least one positive, at least one negative, maybe some zeros thrown in. And then what we said is this looks like it's up in some direction, down in some direction. Maybe, if you're in 5 dimensions, these pictures aren't doing it justice. But there's at least one direction where it's an upward pointing parabola, and another direction where it's a downward pointing parabola, so for sure it's a saddle point. And then there were semi-definites where we allowed it to be 0 for some X's. And 0 for some X's here.
So, do quadratic forms, are they not allowed to contain constants, or do we like...
No, they're strictly quadratic. It's a homogeneous quadratic, like the ones we
Okay.
wrote down the other day.
Okay.
So what I want to do today is talk about how we can apply this to our calculus problems. And you have a few web works, I believe, where you're supposed to identify what sort of critical points you have, correct?
Yeah.
So that's what I'm going to show you right now. So let's, in particular, do the 2x2 case. Because most of your calculus applications will be in 2 dimensions. Some maybe will be 3, but most will be 2. So if you have a 2x2, then you're starting off with some quadratic that looks like this for some numbers a, b, and c. A having nothing to do, maybe I shouldn't use capitals, A having nothing to do with my matrix, so maybe I'll put little letters. So we said you could either complete the square or you could do the matrices if you wanted to figure out how to make this work and see what the D was. You want me to do it with matrices or you want me to do it with algebra? So presumably you guys can do the completing the square the same way we did it with numbers the other day, so I'll do it with the algebra here. So we're looking at the symmetric matrix with an A there, B's there, and C here. All right, that corresponds to this quadratic function. All right, so let's first of all suppose A isn't 0. Then what would we do if we wanted to put this in echelon form? So if A isn't 0, we have a pivot there, so we can reduce it to echelon form by keeping the pivot, and then what do?
Divide by.
So what do I multiply this row by to add to this?
B over 2A? Oh wait.
No, 2.
Oh,
B over
2B.
A.
Okay.
B over A.
B over A with a negative,
Right.
so I get add, so I may take the first row, leave it alone, and multiply it by negative B over A and add it to the second
That
row.
looks familiar.
Right?
Isn't that?
So negative B over A times A plus B is 0. Negative B over A times B plus C is that. Well, so now remember, if I want to write my matrix A in LDL transpose form, and I did this elementary operation, what do I have to do to get L? L is the inverse of this guy, remember?
Yeah.
I went through that several times on Wednesday. So I'm going to have A is L times this guy U, where where L is the inverse of this. So that's 1 B over A, and then 1. And we're supposed to try to see it in terms of seeing L transpose here. What are we supposed to do next?
Make it.
We want a 1, and we want a 1. So remember, we want to factor out the diagonals and make our diagonal matrix here. So I want to factor out an A there. And what will I be left with? I'll be left with 1 B over A. That's nice. And then what do I want to factor out here to get a 1?
C is B squared over A.
Just this thing, which happens to be AC minus B squared over A. Does that AC minus B squared ring a bell? It's the determinant of this matrix. Very interesting. So here's L, here's D, here's L transpose. So understanding the quadratic, okay, now you're going to complain to me that I've only done the case where A isn't 0.
With A is 0, it's not a.
So what if A is 0?
Which X and
Then you
Y
already have
four.
So what if I had this matrix?
Your elementary operations, which is the row.
Hmm?
0, 1.
You can just switch around.
So can I actually, well, I don't want to, I'd rather not do switches if I can avoid it. Can I actually write it as some lower triangular matrix
Can you write it?
times, I don't know.
Not if you want to get, I don't think you can if you want to get the pivot up in the top row.
We could add,
Unless you consider the pivot from the other side, from the right.
So is there,
if you took like B over B as the lower thing and added it to the top one, you could get
Yeah,
one.
but then you would be doing something in the upper triangular.
right, so in fact, you can't do this for this matrix. You cannot, you have to do a row switch in order to get this guy in echelon form. And once you do a row switch, you're no longer getting it in the form of L, DL transpose. You're no longer going to have a lower triangular here if you're doing row switches. So I've sort of cheated you. What if A is 0? At this point, I'm going to resort to just saying, what can we see from the algebra here directly?
Then it's not like that kind of quadratic anymore.
It's still a quadratic.
No,
It's still a quadratic unless everybody's 0.
but it solves to be one
So
thing.
if I
You're not
have
gonna have two
0
two quadratic
here,
terms.
I have 2bxy plus cy squared, and I'm saying you can see immediately that this is going to be a saddle point unless b is also 0. Look at this, you can factor out a y.
Yeah.
So I'm claiming that unless b, so we have a flow chart now. It's starting to be like, so if b is 0, what happens? Then my quadratic function was just cy squared.
Which is always positive.
Well, it depends.
Well,
Now, of course, if c is 0,
then you just zero.
Then it's a point.
Then the game's over. Yeah, okay.
I mean, you have the 0 function. We're sort of done, right? It's just 0 for everybody. What if c isn't 0?
Then it's either positive or negative, depending on if c is positive or negative.
It just becomes like a function of c, so it's in the zy plane, it's just a parabola, and that parabola.
So it's either an upwards parabola
Or down.
or a downwards parabola. So it's either positive semi-definite if c is positive,
Or negative.
positive semi-definite. Why semi?
Because the other one could be.
Because there's some place to.
Because I don't have x involved at all,
Right.
right? So if I just take a vector of the form 1, 0 and plug it in, I get 0. And if c is negative, yeah, it's sort of looking more like
Negative.
troughs. If c is negative, it's negative semi-definite. Okay, so that was sort of, okay. Now what happens if b isn't 0?
Well, b could be positive or negative. I don't think you
Does it
can-
matter?
No.
As long as b isn't 0, then I'm claiming that I can make this either positive or negative by choosing x and y appropriately. For example, choose y to be 1,
Right.
and choose x so that this gets very positive. Right? If b is negative, make x really big negative. If b is positive, make x really big positive. Then this is going to be positive times positive for that x and y. But I could also make it positive times negative. Still having y being 1, I could choose this to be extremely negative, no matter what c is. Fixing y equal to 1, no matter whatever c value is, I can choose this to be a huge negative number so that this is positive and this is negative. So I'm claiming you can just by inspection make this be indefinite because you've chosen, you can explicitly find x's and y's that are going to make them positive and negative. What happens in this story? Well, what do we see? So, both positive. So we're looking at these two numbers. Those are the diagonal entries of our matrix. If A is positive, so let's do it this way. Let's look at the determinant. Suppose it's positive. So So you have your symmetric 2 by 2 matrix, suppose it's determined as positive, then what are the signs of these going to be? A and positive over A, the sign of A. So when A is positive, what do we have? Positive, positive. So what's the quadratic form if the diagonal entries are both positive? Positive definite. Which means A corresponds to a minimum. Suppose A is negative. Negative, negative. Negative definite. That means we're at a max point. Suppose the determinant is negative. What happens? If this is positive, this is negative. If this is negative, this is positive.
It's saddle.
They have opposite signs, so it's indefinite, and I have a saddle point. Now, what happens back in this case? What if A is 0? What does that mean happens to the determinant?
Goes to negative b squared.
It's negative unless
B is 0.
B is 0 as well. So if A is 0 but B isn't, we're in the case where the determinant is negative and we got a saddle and we already decided that.
Can you really consider the determinant because A is 0, then that means you would be dividing by 0 in the matrix?
As it goes.
No. But I'm saying we did a separate argument independent of that stuff in the case when A was 0, and we discovered that as long as B wasn't 0, which means this number is negative, we discovered it was a saddle. So I'm saying this flowchart is consistent in the case even when A is 0. I'm still able to say it's correct that if the determinant is negative, I have a saddle point.
Okay.
However, there's another case here. What if the determinant is 0?
And then b squared equals AC.
So if the determinant is 0, I have an A and 0,
Then we're in trouble.
or I have the case there where we didn't know what was going on, and the final answer is going to be, you don't know. And I'm going to show you some examples today when we actually work out examples where we have to deal with the inconclusive case. But this is a shortcut for 2 by 2 so that you don't have to go through all this rigmarole every time, right? If you have a 2 by 2 matrix, you just know by basic sign analysis, look at the determinant, look if it's not negative or 0, then decide what's going on by looking at the sign of A.
Can you do that for like a 3 by 3 too, using the determinant?
You need a lot more, there's a lot more cases. So for 3 by 3, I'm going to tell you have to actually do the completing the square and figure out what the D's are. Yeah, but there is some linear algebra going on that maybe we'll talk about later, but for now, I'm not going to go there. So the application for calculus now. So I will actually give you a proof of this on Monday, but you're spared that for today. Basically, where is this quadratic stuff coming from at a critical point? Well, I told you that if you have a function that is, say, C2, twice continuously differentiable, then you have something like Taylor's theorem that you guys remember from single variable calculus. You have some expansion like this, that if you're at a point A, and you take a relatively small displacement vector h. This should remind you of linear approximation. Well, there's the linear term that we had with the derivative. And then there's going to be a quadratic term, which I'm going to write script f, script h, that's an h, script, and the h stands for Hessian, not named after a literary character, literary author. So you compute the Hessian matrix at the point A, and you make it into a quadratic form. I'm going to show you how you do that in a second. This is going to be the quadratic form instead of script q. It's going to be built out of the second derivatives of f. And then there's an error, just like we had with linear approximation, where the error goes to 0 faster than not h now, but h squared. So I will show you why this is true on Monday. What happens at a critical point? This is 0. This is a constant. So at a critical point, what f is doing near the point A is determined by this Hessian term. So we want to understand what this quadratic form is, and that's going to be exactly fitting what we just talked about here for the two-dimensional case, or in the general case there. So here's how you do this quadratic form script h. Here is script h of f at A. Start by taking the second partials of f. So we have all the possible partials with x1 and the various variables. Then you do similarly all the partials with respect to x2 and one of the variables. And so on, and so on. And then at the end you have the second derivative with respect to xn. I'm not writing all the stuff, obviously.
So we're assuming this is to a R function, like just an R function?
Yeah, it's mapping to R, right. All this Max-Min stuff is, we're doing scalar functions, ready, done. So these are all evaluated at A. I don't want to write of A everywhere. Now what do you notice? This is called the Hessian matrix of F at A. It's like the derivative of F, except it's second order derivative. It's symmetric whenever f is C2. So remember, these are the same. So this is symmetric. Because f is C2. And the way you're going to use this symmetric matrix to build the quadratic form. So the Hessian builds you this script h by doing H transpose Hessian matrix as your symmetric matrix times H. So this is the symmetric matrix A. So everything I've been telling you about for symmetric matrices, you're just going to crank the matrix of second partials at your critical point, and then you're going to apply what we've done. Okay, so the mystery is why there's a Taylor's formula like this. But once you have the Taylor's formula with this matrix of second partials, then you just turn the crank and do what we've been doing with the linear algebra. So I propose that we do some concrete examples. Any questions on this?
Wait.
Notation is horrible. but I believe I'm being consistent with the book for whatever good that is. So hash written out is standing for the matrix, script H is standing for the quadratic form, built on the symmetric hash. All right, so let's go back to the example we did the other day and see what kinds of critical points it had. And then if we have time, which I think we will, we'll do another example as well. So you guys will either recall or scurry to your notes and remind me.
Here we start this here.
I had chipmunks in the other class, so that's why I was scurrying.
What?
So we had the other day the function x squared minus, I know I wouldn't remember it, minus 3x squared y plus y cubed. Remember that we did this? We did it on the square that went from -1 to 1, but I'm just going to just look for critical points at this point. So we found critical points, so 2 days ago I think it was, 3 days ago?
Class period.
K days ago, where K is something between 1 and 12. We found the critical points by, first of all, taking the derivative and saying the derivative had to be 0 at the points. Minus 3x squared plus 3y squared. So these were our partials. And I believe we found 0, 0.
If we didn't, we are in trouble.
And I believe we decided that you could have y being a third. Coming from this equation, x is 0 or y is a third. And then this one told us that x had to be plus or minus y. So I believe that's what we actually had the other day. And then we did bunches of stuff on the frontier of the square. I'm not caring about that today. My question to you now is, what does the second derivative test, namely this saying our function at the critical point looks like this when we use the Hessian matrix for our symmetric matrix? So what's the Hessian matrix going to be for this? S of F at, well, let's do it at xy first. So I need to take partials of this, 2 minus 6y, then partials of this,
Oh, sorry.
Minus 6y.
whoa,
Oh.
this is wrong, isn't it? We're taking the partials of this with respect to x,
And it's partial the other one with respect to that.
Yeah.
and then with respect to y.
Minus 6.
Okay, so I listened. Okay, and then partials of this guy,
Negative 6.
Wait.
Yeah.
Oh, it's x2.
right? So I'm taking second partial with respect to x, means I take ddx of this. Mixed partials, second derivative with respect to x and y is partial with respect to y of this, which should equal the partial with respect to x of this, and they do agree. And if any of your problems you're doing, they don't agree, you've screwed something up.
What was the condition for when they wouldn't agree again? Because remember we found
Non-C2.
Okay.
So any applications we're doing are nice functions here. We're not doing weird stuff for this thing.
I know this doesn't exactly make a difference because it's C2, but the top right one is actually df of dy and then times by dx, one over, like,
No, did I screw it up?
right?
Yeah, you're right. The way I set it up there, you're right. It is,
Okay.
so I actually, yeah. But, so I was thinking about it the other way around, right? But because it's C2, you can think of it either way and you're gonna get the right answer, but you're absolutely right, actually. I was thinking about partial sub xi, sub xj in that order just because that was easier to think of the matrix IJ, but you're absolutely right. All right, so what happens at our three critical points? At 0, 0, what do I get?
0. No.
Not quite.
2.
2, 0,
0,
0, 0. Well, that's going to be falling into which classification?
Positive semi-definite.
Inconclusive.
The first one.
Inconclusive.
What? I thought it was positive semi-definite.
Right, it is positive semi-definite, but notice I never put the semi-definites here because we don't, in fact,
No doubt.
it's going to be the case that when you have determinant 0, whether you're positive semi-definite or negative semi-definite, you can't conclude anything.
Okay.
So I'm going to show you that in a second. But you're right, this is positive semi-definite, but this is the test is inconclusive. And I'll go back to that. Remind me when I'm done with this example, Matthias. What happens at either of the critical points? Well, what happens when we put in 1/3, 1/3?
We get
You
a
get a
0, -2, -2, 2.
Yeah.
And what happens if I put in negative 1/3, 1/3?
You get 0,
You're good at that, 0.
2.
2, 2,
2.
2.
The 2's have it. Well, all right. So what do we see? What's the determinant?
4.
Not negative 4.
Minus 4.
Am I confused?
The first one is negative 4.
No. 0.
I was just doing the second.
Because it's
Matter.
0 times 2
I'm doing
minus
both
negative
back.
2
Yeah,
and
minus
negative 2.
2. Yeah.
Turn your head upside down.
I can't do that.
0 minus
Yeah.
4. So both of these put us in the
In
Saddle
the
point.
saddle point form.
saddle point category. So we've got 2 saddle points and I don't know.
Wonderful.
How about we find out what to do with that?
So when you get an inconclusive result, you really have to go back and just look at the function near the point. Well, luckily for us, 0, 0, I can look and see when x and y are near 0, I know what, I can get some idea of whether I have a max, a min, or a saddle point. Do you see what I can do? Near 0, 0, consider, well, what particular points would be good to consider? What happens if you consider points x, 0? What does the function do?
X squared.
So, it goes up.
Positive.
What else could I consider?
0, y.
And what happens now? It's 0y.
Y cubed.
And what do we know about y cubed?
It's
It's
it goes
both.
up and
It does both.
Yeah.
So it has to be a saddle point. Just the y cubed was enough to tell you it had to be a saddle point.
Right.
Because when x is 0 and you vary y, it's both positive and negative. Ergo, saddle point. Well, this is boring. All 3 critical points are saddle points. How dare it?
It was your example.
So now back to Matthias's issue. So the warning here is, for even when this second derivative stuff is positive semi-definite, or negative semi-definite, it's not going to matter. It's still going to be inconclusive. So consider a function like this. This part makes it have a 2 in the upper left corner, right? Just like we had here. This 2 came from the differentiating the x squared. But now suppose I put a y to the 4th there. with a plus or a minus? Well, the y to the fourth is going to give me what when I do second derivatives at the origin?
A squared.
12
y
x
squared.
12 y squared.
What?
But add 0.
It's gonna give you a zero.
Give me 0. So the Hessian matrix here at 0 is going to be 2, 0, just like we had for this example. Regardless of whether there's a plus or a minus.
Oh no.
Yeah.
So if it's a plus, what kind of critical point is it?
It's,
Minimum.
yeah.
Because both these
Oh.
terms are positive
I was gonna say
otherwise.
positive, definitely.
What if it's a minus here?
Saddle.
So just knowing the second derivative isn't good enough when the determinant is 0. You just can't tell what's happening with the higher order stuff. Okay? And of course I could have even the 0 matrix for this Hessian if I put a cube here. Right? If you put higher order terms, you'd have all partials 0, when you took second derivatives. And then you don't know anything at all, just from the second derivatives being 0.
Goodbye.
Okay, so that said, actually, let's do another example. Maybe I'll luck out and find something that isn't a saddle point. So this is like something we were doing the other day, so I figured I'd revisit it. Suppose I took sine x plus sine y plus sine, now just to make it different, I'll do x minus y. It's a little different from what we had the other day. So how do we find critical points? So df dx cosine x plus cosine x minus y, df dy cosine y plus minus cosine x minus y, right?
Unfortunately.
So what have we got for critical points? So if we set these both equal to 0,
Cos equals negative cosine y.
so do we have any?
So
It's a little different from what I did the other day when we had a plus here.
x equals y.
So if I add these two terms, I get cosine x plus cosine y is 0.
So one's equal to the negative of the other.
So one's equal to the negative of the other. But,
But then there's some sort of
so,
shift.
so how can that happen?
Yeah.
If they're pi
y
away
equals
from each
pi
other.
minus x.
I said
So if you
x
think
equals
unit
pi
circle,
It's like when they're pi over 2.
when they're pi apart.
No, because when they're pi.
no.
No.
When they're pi apart, they're the same.
These guys have opposite cosines.
Yeah, so it's pi minus x.
Pi minus.
Yeah.
So this is going to say that y is pi minus x.
Oh yeah.
Or,
That's what you meant to say.
That's why we get pi plus y.
is,
Yeah.
So in fact,
Thanks.
agreed?
Yes.
I'll give that to you.
So in this case, what do I get when I say cosine x plus cosine of x minus y is 0?
It's cosine x plus cosine
X.
2x minus pi.
So what's x minus this guy? It's 2x minus pi.
Which is the same as
Or I would have cosine x plus cosine of
Negative
x minus this.
pi. So negative pi. Which would be -1, right?
So this would seem to say x is 0 or 2 pi, etc. And this would say
What is
yeah.
negative 0?
Well, okay. X equals.
So this is the same as
What are you doing?
cosine x minus cosine of pi minus 2x.
Which is
So-
minus cosine.
Oh wait, no,
No,
cosine's
it's plus.
even.
It's plus.
What are you doing?
It's plus.
Yeah.
I skipped a step. But that's cosine of pi minus something
It's cosine of 2x, right?
is the negative.
So
Alright?
X
Cosine
equals.
of, that's what we were just saying here. Cosine of pi minus this is the negative of.
So now we turn to a quadratic thing.
So, right, so you can say cosine of 2x is 2 cosine squared of x minus 1. And you get a quadratic to solve, which probably, stuff like this will show somewhere in your homework, no doubt. So for this to equal cosine of x means so 2 cosine x minus 1 times cosine x plus 1 is 0. Did that work?
Yeah.
No.
No.
Plus minus. Now does it work? 2 cosine squared plus cosine minus 2 cosine minus 1. So either
Yeah.
cosine x is 1, we already got those,
Or it's negative.
or cosine x is minus a half.
And that happens sometimes.
That does happen sometimes. It happens over in this quadrant somewhere. And so x is actually going to be 2 pi over 3.
That wasn't funny. We had different sense.
And then y would be either pi minus that. I mean, there's infinitely many, but then the y's would be pi minus that, or pi plus that.
5 pi over 3.
Plus that is like,
5 pi over 3.
3 pi over 3 is 2 pi over 3 is 5.
oh, well, that's interesting. That pi minus x
5 pi.
plus, and if you do this one, you're gonna get the other one.
If you're getting this confused on these problems, how do you expect us to do them?
Well, I'm rushing is what I'm doing. So,
He's Russian. He's Russian, that's right.
so we would need to look at second derivatives to look at the Hessian. And there's an interesting critical point at 0, 0. And then, for example, we would have 2 pi over 3, pi over 3 as another, and there's lots of them, but this would be 2 typical ones to look at. Let's just double check. Yeah, that's right. Cosine y minus, yeah, so this checks. So let's look at the Hessian quickly at these 2 points. What's the second partials?
Good question.
Huh? There
Let's see,
would
we got
be
negative sine
sine
x
negative
minus
sine
sine x minus y
So negative sine x
minus
minus
sine x.
sine of x minus y. And then the next
and then
one
I do
would
the
just
y
be
partial.
sine of x minus y.
Question, why 0, 0?
Negative sine
Well, no, because the negative, then the chain rule on the negative
Oh,
one.
0, 0,
Right.
it's
It's
zero.
not pi.
It's 0 pi.
Yeah.
Right?
Oh, it's Jordan cosine sine.
Yeah, 0. Yeah, 0, 0 is definitely not right. Thanks. Okay, back at the ranch, sine of x minus y, and then,
And negative sine y. It's like symmetric to the what we already got.
no, it's anti-symmetric. Well, it's not either,
Well,
because of the minus sign.
because of a minus sign.
So you're gonna pick up,
Wait, is it? Are you
It's
sure
still
it's not
minus.
negative? Yeah.
minus sign.
It's minus,
Right.
minus, minus.
Okay, so what happens at
Minus minus line.
0 pi, and what happens at pi over 3, 2 pi over 3, pi over 3?
Well, 0 pi is 0.
So I get 0, 0, 0, 0,
Something.
It's all 0.
it's all zeros.
Yeah.
That's useful.
That's useful. What happens at 2 pi over 3, pi over 3?
Yeah, you can do that one.
So let's see, what's the sine of x minus y? Well, that's sine of pi over 3,
which is
that's square root of 3 over 2.
It's
yeah.
negative square root of 3 over 2 for the top one.
And then we
Because the
have,
signs are equal, right? So it's just negative square root of 2 squared. So negative root 3.
That's true.
Yeah,
Makes
negative
an
root
excellent
so
point.
this is 0, isn't it? Whoa.
No.
No, it's
It
negative.
should be 2,
It's
whatever.
negative root 3, right?
It would be, yeah, 2 root 3 over 2.
Sine of 2 pi over 3,
Those are going to be the same
Minus
value.
sine, it's,
Because
you have,
what?
Yeah, it is.
and then you're subtracting the
But it's
same,
negative, it's negative.
You're subtracting
Yeah,
the same
so
thing,
it's
so it
same
becomes
as-
negative 2
But it's
square root of 3 over 2.
Negative
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 root 3.
root 3 over 2.
Minus 2 pi over
root
3.
3, right?
Whoa, whoa, whoa.
Yeah.
What?
oh,
It's,
so it's that.
thank you, there you go. It should be the same thing for the other one too, right?
Yes.
Yeah. Because,
So what happens here?
Take the determinant.
Determinant
3 minus.
is
3
3 minus 3
minus-
fourths.
Which is going to be positive.
just for today only.
And then
And it's positive,
But
it's
A
going to
is
be a
you have
negative.
negatives
maximum.
here,
So it's sad.
It's a maximum.
so it's
That's
maximum.
what I
It's a
said.
local
That's
maximum.
what I said. I almost said sad.
Now, the 0 one is a little disappointing. So what you would have to do, and I will pick up with this at the very beginning on Monday, just in the middle of all of this, that's all I'm going to do, is I'm going to say, okay, what's that function doing near the point 0 pi? How can we decide that?
That's the entirety of class.
No, that's not. That's what I'm going to start with, but I'm not going to recap all this other than saying, let's look at that function near 0 pi, and then we will go on and
So why did the negative in front of the root 3 matter to determine what's a local max?
because we bifurcated if the determinant's positive, the sign of A
gotcha,
determines it.
gotcha.
Okay,